Good morning, students. Today the topic is WKB approximation. Now, what is WKB approximation? It is known as the Wenzel, Kramers and Brillouin approximation according to their name, Wenzel, Kramers and Brillouin. This is known as the WKB approximation. It is a technique. It is a technique for obtaining approximate solution of one-dimensional Schrodinger's equation. It is a technique for obtaining one-dimensional solution of one-dimensional Schrodinger equation or a wave equation which can be separated into equations each of which contains only single independent variable. So it is a very important topic in quantum mechanics, and actually it demonstrates the connection between the quantum theory, the classical theory, and the quantum mechanics. It is basically show you that there is a connection between the old quantum theory, the classical mechanics or the classical theory, that is the old quantum theory, the quantum mechanics, and the modern quantum mechanics. So actually it is based on the expansion, that this process is based on the expansion of the wave function in powers of h cut. So WKB approximation is a method which demonstrates you that there is a connection between the classical quantum theory and quantum mechanics. It is based on the expansion of the wave function in powers of h cut. Now the zero, the first and second powers of h cut respectively give the classical, that is the power of h cut. When the power of h cut is 0, it gives us the classical approximation. When h cut, that is the power of h cut, is 1, it gives us the quantum theory. And when h cut, the power of h cut, goes to 2, it gives the higher order results. So this WKB method is also known as a classical approximation, since it gives the classical result when h cut is set 0. This method is applicable. Now this is a very important term, or this is a very important, you should note it, that this method is applicable only when the potential is slowly varying. So whenever you got a problem in quantum mechanics, and where do you apply this WKB approximation, it can give you as a short question as well, that whenever you have to apply WKB approximation, so the answer should be that WKB approximation is applicable only when the potential is slowly varying. So just remember this. Now let's move on to the method, that is the WKB method. As I told that this method is applicable only to one-dimensional Schrodinger's equation. So we take a one-dimensional Schrodinger's equation of a particle moving in a region of constant potential V0. So we are taking a particle, a one-dimensional Schrodinger's equation of a particle moving in a region of constant potential V0. And the equation should be, as you know, that it is d2 psi dx2 plus twice m by h cut square e minus V0, capital E minus V0 psi equals to 0, and this should be our equation number 1. Or you can take this equation as, you can reduce this equation as what we have tried earlier, that d2 psi dx2 plus twice m by h cut square and e minus V0. These all terms are constant, so you can write it as k square. So you can write it as k square psi equals to 0. Let it be equation 1. Remove this. Let it be equation 1. Where, as we know, that k square equals to nothing but twice m by h cut square e minus V0. here V0 is a constant, as I have told that this is the equation of a particle which is moving with a constant potential V0, and this is the one-dimensional Schrodinger's equation. Now, let us solve this equation. So, our problem is to solve this equation. To solve this equation, its solution is psi equals to e to the power plus minus I k x. Let it be equation 2. Now, if the potential is not constant, as I have told you earlier, that you have to apply this WKB method. You have to apply this WKB method whenever the potential is slowly varying. Whenever the potential is slowly varying. So, if the potential is not constant but varying slowly, then this k in equation 1, then this k in equation 1 should be a function of x and is given by k square equals to twice m by h cut square e minus v of x. So here I am considering that the potential is slowly varying, and let it be equation 3. Let it be equation 3. Now, writing the solution of Schrodinger's equation in the following form and substituting in equation 1. So now we are substituting in equation 1, that is, we have taken psi, the solution of this equation 1 is psi equals to e to the power plus minus I k x. So I have to find out the value of d psi dx and then d2 psi dx2. We have to find out the value of d psi dx as psi equals to. So writing the solution of Schrodinger's equation in the following form, the form is psi equals to e to the power I sx by h cut. So this is the form I have taken. Now this is the form I have taken for the solution of the equation, that is psi equals to plus minus e to the power I sx by h cut. This is our equation 4. Why I have changed the solution of psi? As because here when I have taken psi equals to e to the power plus minus I k x, then actually I have noted that the potential is a constant. But as I have told you earlier, that this WKB method is actually applicable when the potential is slowly varying. So I have taken that k square equals to twice m by h cut square into e minus vx. So here you can see that the potential is slowly varying, as because that term of k square has been changed. So I have to change my solution of psi, that is, I have taken e to the power I sx, that is, s is a function of x, sx by h cut. Therefore d psi dx should be I by h cut e to the power I sx by h cut, and then the differentiation of sx, so it will give me s prime of x, that is ds dx. So this is the value of d psi dx, and then find out d2 psi dx2. Then find out the value of d2 psi dx2. Again, it will be I by h cut, keeping e to the power I sx by h cut constant. then find the differentiation of s prime x, that it will give me s double prime of x, then plus I by h cut, keeping s prime x now constant. Now I am finding that the differentiation of e to the power I sx by h cut, so it will give me I by h cut e to the power I sx by h cut, and then again s prime of x. So now this can be done by yourself also. So I find that d2 psi d2 psi dx2 is actually, therefore, I by h cut e to the power I sx by h cut. S double prime x means d2s dx2, d2s dx2. Now this is here, I get I into I, that is I square. So minus 1 by h cut square. This is minus 1 by h cut square s prime x whole square, that is e to the power I sx by h cut, and s prime x, that means ds dx whole square, and then plus, now this is the whole value of d2 psi dx2, so this value plus twice m by h cut square, twice m by h cut square e minus vx into psi, that is e to the power I sx by h cut, is actually equals to 0. So I have putted the values of d2 psi dx2, d psi dx, and then also the value of psi. Now cancelling e to the power I sx by h cut from all the terms, I can cancel out e to the power I sx by h cut from all the terms. What I get? I get ds dx whole square, ds dx whole square. And now another step can be done here, that multiplying this equation by minus h cut square, multiplying this equation by minus h cut square. So when I am multiplying this equation, this term with minus h cut square, it will give me, it will become plus it ds dx whole square. So it will give me ds dx whole square. That is our second term. Now here, as I am multiplying this with minus of h cut square, so it will give minus I h cut, minus of I h cut d2s dx2, it will give minus I h cut d2s dx2, and then here it will be minus of twice m. So I can write it in the right hand side as plus twice m e minus vx. So it will be e minus vx, or we can write it as ds dx whole square, ds dx whole square minus I h cut d2s dx2, and then it can be written as minus k square h cut square equals to 0, and let it be equation 5. Let it be equation 5. So equation 5 becomes ds dx whole square minus I h cut d2x dx2 minus k square h cut square equals to 0. This is our equation 5. Now the solution of this equation, gives me the function s of x, the function sx. So expanding sx in powers of h cut, that is, we get sx equals to s0x plus s1x into h cut s1x plus h cut square s2x and the higher order terms. Now here I have neglected the higher order terms as because that since h cut is small, the terms containing h prime, h cut square and higher powers of h cut can be neglected. So we have neglected the higher order terms. Therefore, neglecting the h cut square term and so on, we actually get sx equals to, so we are keeping these two terms, that is s0x plus h cut s1x. Let it be equation 6. So far I am getting the equation 6, that is the function of functional value of sx as s0x plus h cut s1x. So now we have to find that ds dx and then d2s dx2 again. So let's find out ds dx. So ds dx should be s0 prime, as s0 is a function of x, so it will be s0 prime plus h cut s1 prime, and d2s ds2 and d2s dx2 should be s0 double prime plus h cut s1 double prime. So let's move on to substituting these values of ds dx and d2s dx2 in equation 5. So now we are going to substitute the values of ds dx and d2s dx2 here in equation 5. So here, by substituting the values of ds dx and d2s dx2 in equation 5, we get, so ds dx whole square, that means s0 prime plus h prime s1 prime whole square minus I h cut, d2s dx2 means s0 double prime plus h cut s1 double prime and then minus h cut square k square equals to 0. So by substituting the values in equation 5, I get this. Now expanding this equation, what we will obtain, we get s0 prime square, s0 prime means ds0 dx, so it will be ds0 dx square, then plus h cut ds1 dx square, that is h prime square ds1 dx square plus twice h cut ds0 dx into ds1 dx. So this is the expansion of s0 prime plus h cut s1 prime minus of I h cut s0 double prime means d2 s0 dx2 plus h prime s1 double prime, that means d2 s1 dx2, and then only minus h cut square k square equals to 0. Now here, after substituting these values, what you can see that here again we have we get the terms containing h cut square. Here again, we obtain the terms h cut square. So it will ds0 dx square minus h cut square k square. Now actually I am retaining this term h cut square k square, and why I am retaining this term of k square h cut square I will explain you just now. And then this term, that is h cut square ds1 dx. So neglecting this term h cut square ds1 dx, as because again I am telling that h cut is small, so the term of h cut square ds1 dx square will be very small. So just neglecting this, and then we have these two terms, and again here is a term which will contain h cut square. So I have to neglect this term also. This term also I have to neglect. So just taking h cut as a constant, I get twice of ds0 dx into ds1 dx, and then comes here, that is minus of I h cut d2s0 dx2. So as because the term contains only h cut term, so we take this term, that is as minus I d2 s0 dx2, and that equals to 0. So here I have actually omitted two terms. One is h cut square ds1 dx whole square, and the other term is h cut square d2s1 dx2. Now here an interesting point that rises, that I have taken this term h cut square k square, that this term is also contains a term containing h cut square, but I have retained this term. Now why I have retained this term? As you can see that my k square, I have taken k square as twice m by h cut square e minus vx. I have taken earlier that k square equals to twice m by h cut square e minus vx. Now then you can find out that the term h cut square k square should be twice m e minus vx. So the term, that is the product term of h cut square k square, actually gives a term twice m e minus vx, and you can find out that this term, that is the product value of h cut square k square, is actually an independent term of h cut. So I think you got my point. So I have retained this term of h cut square k square. Okay. So now my equation stands here, that is ds0 dx square minus h cut square k square plus h cut of this, and let it be equation 7. Now for this equation 7, to be valid, the coefficient of each power of h cut, must vanish separately. Now here comes the Wkb approximation method, that for equation 7 to be valid, the terms of the coefficients of each power of h cut must vanish separately. So I get two separate equations. One is ds0 dx square minus h cut square k square equals to 0. So this is my equation 1, and the other equation should be in the parenthesis as twice ds0 dx ds1 dx minus I d2s0 dx2 equals to 0. I think you all can follow this. So we get two equations. One is ds0 dx whole square minus of k square h cut square equals to 0, or you can get ds0 dx. You can get ds0 dx equals to plus minus of k h cut, and this is our equation 8. So this is our equation 8, in which I get ds0 dx equals to plus minus of k h cut. Okay. Now the other equation. What about the other equation? The other equation, I get the other equation from equation 7, from the second part of equation 7. So let's move on to the second equation, or the second part of equation 7, and I get twice ds0 dx into ds1 dx, twice ds0 dx into ds1 dx minus I d2s0 dx2 equals to 0. Let it be equation 9. So far I have splitted this equation 7 into two independent equations and equating. And how can I get these two separate equations? I am equating the coefficients of h cut. I am getting this equation, these two equations, that is equation 8 and equation 9, from equation 7 by equating the coefficients of h cut to 0. So by equating the coefficients of h cut to 0, one equation, I get this equation as ds0 dx whole square minus h cut square k square equals to 0. From this you get ds0 dx equals to plus minus of h cut k. Now this is our equation 8, and the other equation, I get the other equation from the terms in the parenthesis as twice ds0 dx dot ds1 dx minus I d2 s0 dx2 equals to 0. I think, Tripti, you get my point? Now proceeding further, from equation 8, I have to find out the exact value of s0. So s0, that is from equation 8, s0, and since this is the function of x, s0 x equals to plus minus integral of k h cut dx, and it becomes plus minus. Now putting the value of k, so what is our value of k? K square is actually twice m by h cut square e minus vx. So the value of k should be twice m into e minus vx whole to the power of half, So this will be, I am putting the value of h cut k as h cut square k square. H cut square k square is our twice m e minus vx, and then so the value of h cut k should be twice m e minus vx whole to the power half, and then the term dx here. So let it be equation 10. So from the equation number 8, I get the value of s0x. Now as ds0 dx equals to plus minus of h cut k, it means d2 s0 dx2. It means d2 s0 dx2 should be plus minus of h cut dk dx. Now here as you know that k should be a differentiable function as because k contains the term vx. So k is a function dependent on x, and so I can get the differentiation of dk dx. Then equation 9, what is our now putting the value, I can put this value of d20 dx2 here in equation 9. So I get, I'm omitting this, removing equation 10. So equation 9 becomes twice ds0 dx. What is the value of ds0 dx? I have found ds0 dx equals to plus minus of h cut k. So putting the value of ds0 dx as plus minus of h cut k, then ds1 dx, and that equals to plus minus of I h cut dk dx. So here I am putting the value of d2s0 dx2 from here. So what happens? I can remove these h cut terms from both sides. I can remove that plus minus terms. So I get ds1 dx. I get ds1 dx equals to I by twice k. I by twice k dk dx. So this is my equation number 11. So already I've taken half an hour of class. How are you feeling, or is it okay for you all? Please comment. So this is the value of ds1 dx. Now integrating this equation of ds1 dx, or integrating this equation 11, I can find the value of s1. So integrating, I get s1 equals to, that is I by 2, and dk by k means ln k. So it will be I by 2 ln k, or I get I of S1, I into S1, that means I square by 2, or that means minus of half ln k, or I can write it as ln k whole to the power minus of half, or e to the power I s1, e to the power I s1 should be k to the power minus of half. So here in equation 12, I have found the value of s1. I have found the value of s1. Okay. Okay. So now restricting to two terms, in equation 6. Now in equation 6, I have written Sx equals to S0 plus h cut of S1x. So restricting only these two terms in equation 6, and it follows from equations 4. Here E minus V for particle in motion, T equals to E minus V. Yes, Prabhat Ranjan Das. Yes. Yeah, that's right. That here I have taken the particle, and the energy of the particle is E minus Vx. E minus Vx, as the potential here is varying, but it varies very slowly. So just remember this these words, that the potential is here, and the potential is not a constant one. It is actually varying very slowly. Okay. So restricting to two terms in equation 6, it follows from equation 4, equation 6, and this of equation 12. That is actually, I am now writing the value of psi. So this very expression which I am deriving right now, and you also are, I think, deriving this equation with me. This equation is deriving, we all are deriving this equation to get the value of psi. So the value of psi should be a e to the power I by h cut. I take psi equals to a e to the power s1x I s1x by I sx by h cut. This was our equation 4. I think it was our equation 4. Let's check me. Yes, I have taken psi equals to, in equation 4, it was psi equals to e to the power I sx by h cut. So now we are confining our derivation or the value of sx with only two terms, that is s0 plus h cut s1x. So the value as a e to the power I by h cut sx, it was our equation 4, and putting the values here, or I can expand it as s0 I am writing here again s0 plus s1x, or it will be a e to the power I s0 I by h cut s0 plus, or it will be e to the power of I s1. It was h cut, yeah. So the value becomes a e to the power I by h cut s0 into e to the power I s1. Now as the value I find in equation 12, that the value of e to the power is1, I got the value in equation 12. So putting the value of e to the power is1 in this equation, I get that becomes a by k to the power half, as because it was k to the power minus half. So the value becomes a by k to the power half dot e to the power plus minus of I integral k dx. And this is equation 13. This is equation 13, as because the value of s0x, was plus minus of integral h cut k dx, and here it was I by h cut, so h cut k becomes only k, so it is integral of k dx, and this is our equation 13. Now here a is a constant, as you know, and the constant k is actually, it was given earlier in equation 3, that k square equals to twice m by h cut square e minus vx. So the general solution will be a linear combination. The general solution will be a linear combination of the two terms, one with a positive sign and the other with the negative sign. Now the wave vector k, as because k square equals to twice m by h cut square e minus vx, so the wave vector k is real, and therefore this solution is actually an oscillatory equation. Just get my point? I think from this equation number 13, here a and k, as you know, as you get there, that these two are constants, but the value of k, I have already taken it as k square equals to twice m by h cut square E minus Vx. So I have already get the value of K, and from the expression of K square, you can arrive here in the conclusion that actually K is a real term. K is a real term, and therefore the solution is oscillatory. Now the probability density in undergraduate classes, you have already done so many times that the probability density as chi star. So the probability chi star, what will be the value of the probability chi star? It becomes mod of a square, k to the power half, and k to the power half again means k, e to the power plus minus I integral k dx. This was the value of psi, and then you have to write the complex conjugate as e to the power minus plus integral I integral k dx. So by taking these terms, or by taking the product of these terms, I get mod of a square divided by k, and this is equation 14. Now from de Broglie hypothesis, we know that P equals to, that is the momentum, P equals to h cut k. So the probability density, this probability density or chi star is actually inversely proportional to the velocity term. It is actually inversely proportional to the velocity term, because as we know from de Broglie's theory that P equals to h cut of k, or P equals to h cut k. So here we can conclude that this probability density is actually inversely proportional to the velocity. Now in quantum mechanics, now here comes the theoretical aspect of this approximation or this theorem, that in quantum mechanics particles can even penetrate classically disallowed regions. That means that in classical theory or in classical mechanics, where the particles do not enter, in quantum mechanics these particles can also enter in those regions, and therefore we have to consider the case E less than Vx. As we know that a particle can penetrate in the region where E is greater than Vx, as because the Vx is the potential which the particle has to overcome. But in quantum mechanics, so we have to, particles can even penetrate classically disallowed regions, which we have to consider, and this is the case whenever E less than Vx. Now for E less than Vx, the basic equation what I have taken as d2 psi dx2, plus k square psi equals to 0, where the value of k square, remember the value of k square is our twice m by h cut square, and then comes the term E minus of Vx. So there we consider that the energy of the particle is greater than the potential value of the region. Now here comes the twist, that if the energy of the particle is less than the potential of the region. Get my point? So the basic equation, that is d2 psi dx2 plus k square psi, should be changed, and it becomes d2 psi dx2 minus of, I have taken another constant as k square, in place of k square, let it be gamma square. So the basic equation turns to be for E less than Vx. Now this is actually an interesting case. where the basic equation turns to d2 psi dx2 minus, let the constant be gamma, gamma squared psi equals to 0. Now, so gamma squared is actually the term twice m by h cut square Vx minus E. So here the potential of the region is actually less than the energy of the particle. So let it be equation 15. Now proceeding in the same fashion, as I have done here, proceeding in the same fashion, I get the solution of equation 15 as psi equals to, the solution of equation 15 as psi equals to some constant, let it be b by gamma to the power half e to the power plus minus integral gamma dx. Just note it down that here a term I is absent. What I get in equation 15, I think in equation, no, that is not equation 15. The solution was here in equation 13. The solution was given in equation 13 as psi equals to a by k to the power half. Now this is b by k. Here I have replaced k by gamma. So the term is b by gamma to the power half. And then in equation 13 it was e to the power plus minus I integral k dx. Here the term changes to e to the power plus minus integral gamma dx, not the I k dx. Here it is e to the power plus minus integral gamma dx. So just this minimum values are changed here. Now here also b is a constant, and I can tell you that the most general solution is a linear combination of the two terms, one with a positive sign and the other is the negative sign. Now one term is actually a, an increasing value, one term with exponentially increasing value, that is e to the power plus integral gamma dx. So it is an exponentially increasing term, and the other term, that is e to the power minus integral gamma dx, it is actually a term, an exponential term with decreasing value, right? Now you can ask me that what will be the case when E approaches, that is the energy of the particle approaches the value of the potential, that is E approaches or E nearly equals to Vx. So what will happen if I have taken two cases independently? One is E greater than Vx, and then I've raised the case that when E less than Vx. Now you can ask me that what will happen if E nearly equals to Vx. Now if E nearly equals to Vx, you can find from the value of k square as well as the value of gamma square that whenever E nearly equals to Vx, both of these terms, that is k square as well as gamma square, tends to 0. So that means k and gamma tends to 0. Consequently, if k goes to 0 or gamma goes to 0, consequently psi goes to infinity, as because psi was for with k value psi, the expression of psi was psi equals to a by k to the power half, and if k moves to sorry, if k tends to 0, that means psi also tends to 0. And if the expression is psi equals to b by gamma to the power half, yes, you have considered is rightly that whenever again for E equals to Vx, gamma, as gamma tends to 0, that means again psi goes to infinity. Yes, Shagorika, I am considering, I am discussing this particular case. Yes, particle would stop when E equals to Vx. So the point at which, so I think the discussion should be that whenever that energy of the particle, whenever the energy of the particle equals to the potential energy of the region, psi goes to infinity. Now it means in quantum mechanics, psi tends to infinity means your theory, that is the Wkb approximation, fails here. Your theory that you can't consider the wave function goes to infinity. So the theory of Wkb approximation fails here, and this point at which E equals to Vx, this point at which E equals to Vx happens, it is the classical turning point. It is known as the classical turning point, since at this point a classical particle would stop. What Shagorika already told, that the particle would stop, but the particle will stop, a classical particle would stop and begin to move in the opposite direction. So what happens to the particle whenever it stops? It couldn't enter further, or it cannot move further. So it has to move in the backward direction or in the opposite direction. Exactly. So this is our classical turning point. Now this is all about the WKB approximation. Now here I have raised one problem in the last part of my discussion, that as you have already both of Shagorika and Satyajit, both of you have pointed it rightly. So this is the case which I want to discuss further, that what is the connection formulas. Now it is necessary to point out that the WKB method can be used in the problems in which we have two regions. This Wkb approximation can be used or can be applied to particles in which there are two regions where the Wkb approximation is valid, but which are separated by a classical turning point. That is the important part of this formula, or this connection formula, that the particle should move in two regions, but there should be an interface, or there should be a classical turning point, that is when E and the potential Vx equals. So I am considering, or I am discussing now the case shown in this figure as as say this is X and this is the potential Vx. Now this is the energy E. This is the energy E. Now there are two regions. Say this is X equals to X1, and in this region E is greater than Vx, and in this region E is less than Vx. Now how E is greater than Vx? Now this is region 1 and this is region 2. Now Now in this region E is greater than in this figure. In this figure, a particle, how will it move in opposite direction, sir? Please explain. How will it move in opposite direction, sir? Please explain. Okay, I'm just now I'm explaining this point. What I have told you earlier, that whenever a particle having an energy greater than the potential energy, it will move through the region. And in classical mechanics, what we have learned, that a particle with an energy less than the potential energy cannot move through the region. But in quantum mechanics, I think I explain you that whenever a particle having an energy less than the potential energy of the region, it also can move. But what is the case, or what will happen if both the energy of the particle and the potential of the region becomes equal? And what from the mathematical expressions I have told, that whenever this E and Vx equals, that means k square becomes 0, k square or gamma square becomes 0. That means k or gamma tends to 0, and it actually, and the consequence of k and gamma turns 0 is psi becomes infinity. Now psi becomes infinity, it is actually not the case to be discussed in quantum mechanics. It cannot happen. So here what we can conclude, that actually for E equals to Vx, the Wkb approximation fails, as because psi becomes infinity. Now, if what will happen here, that is in the region when E and Vx becomes equal, actually when E equals to Vx, the particle stops its journey, as it cannot move again forward, but it can move in opposite direction. It can reflect it, actually it is the reflection case, it can reflect it back. Okay, now this is the connection formula, actually what I have to discuss, that in this figure, a particle having energy E. Now this is the Vx, this is the potential. In WKB approximation, I have time and again told you that here the potential varies very slowly. So I have taken the potential of a particle, and it changes very slowly. Now in one region, as this is the energy of the particle, the energy of the particle is E. So in this region, you can find out that the energy E is actually greater than the potential. So in this region, the energy E of the particle is greater than the potential. And in region 2, the potential Vx, the potential of the region Vx is actually greater than the energy of the particle. So in region 2, actually E less than Vx, and in region 1, E is greater than Vx. And here, this is the classical turning point. Now, this is the classical turning point, that is at x equals to x1, E and Vx equals. This is the point of interest. Now that at x equals to x1, the energy of the particle and the potential of the region is actually equal. So what happened? Now in this figure, a particle of energy E encounters a potential Vx. Now region 1, that is E greater than Vx, and whenever E, that is the energy of the particle, is greater than the potential of the particle, we explain it, or we can term it as classical region, as because in classical mechanics, particles only move in that region in which the particle's energy is greater than the potential energy of the region. So here as E, that is the energy of the particle, is greater than the potential energy of the region, this region is termed as the classical region. And now the second case of our derivation, that is when E less than Vx. Now in quantum mechanics, particles can penetrate into the region in which the energy of the particle is less than the potential of the region, and this is the non-classical region. So this is our non-classical region. So region 1 is our classical region and region 2 is our non-classical region, and these two regions, that is the classical region and the non-classical region, is actually separated by a classical turning point x equals to x1, that is the point corresponds to E equals to Vx. It is also necessary to mention that the above method can be applied only. It also necessary to mention that the above method can be applied, that is the above method means the Wkb approximation method is applied, it can be applied only if we can find a way to extend the Wkb solution from one region to the other through the turning point, or if we can obtain a connection between the Wkb wave functions in the two regions. So it is you have to focus on this particular line which I have told you just now, that the approximation method of Wkb or the Wkb approximation method is true, or you can apply it in this particular case if you found any connection between these two regions, that is if you can find out a connection of psi in this region 1 and region 2. Okay, now I am actually discussing the figure here. The figure as a particle having a potential Vx, having a particle having a potential, okay Dolly, a particle having a potential Vx is actually moving in a region a particle having an energy E is moving in a region in which the potential Vx slowly varies, as because whenever the potential varies slowly, only then you can apply this Wkb approximation, as I have repeated so many times. Okay, so now in this figure I get two regions. One is when E greater than Vx, that is the energy of the particle is greater than the potential energy of the region, and the other is E less than Vx, in which the energy of the particle is less than the potential energy of the region. Now, as in classical mechanics, which we have taught earlier, that a particle only moves in a region of potential V whenever its internal energy or its own energy E is greater than the potential energy of the region. So this region in which E is greater than Vx is known as the classical region. Okay, and now here in which the energy of the particle is less than the potential energy of the region. Now in quantum mechanics, we have discussed in our BSc classes as well, that if a particle having an energy less than the potential of the region, it can move. So this is the region that is in which E less than Vx is actually a non-classical region. And now this is the point, this is the point of contact, or this is the point of interest now, that when x equals to x1, that is at x equals to x1, E and Vx equals. So this is the classical turning point. Now, here which I have told you that we have to find out, we have to make sure that if you are going to apply this WKB approximation in such a case, that okay, Debraj, I should discuss it. In such a region, that is in one region there is a classical region and the other one is the non-classical region, and your particle is moving through these regions. So you can apply that WKB approximation, as because here again the same representation, that is the potential is slowly changes. So you have to apply that approximation, that WKB approximation, but keeping in mind, but you have to keep it in mind that you should make some connections, or you should establish some connections of the wave function in these region 1 and region 2. Otherwise, this discontinuity appears here. So some connection equations should be made here to make WKB approximation valid. Okay. Actually, Debraj, a very pertinent question you raises, that how will we consider that slowly varying, that potential is slowly varying, or is there any limit of the potential? Yes, there is a limit, but here what we are discussing here, that in quantum problems or in problems in our daily life, we get some potential, or some potential in some region varies very fast. Actually, this is a as because this is an approximation method. Now, why, you know that why we are applying these such approximation methods? These approximation methods are meant to reduce the tediousness of our problem or of our solution, that if you are considering a potential to be continuously vary, you have to apply Schrodinger equation for the separate potentials of the region, and then you find that you are actually in a dilemma, that whether to leave this problem or to go through this problem. So here comes these approximations, and these approximations are nothing but they are mathematical approximations, and here some physical aspects of the problems are given, that if you can find, and this is the judicious knowledge, or this is the actually this is the whenever you are going to apply any approximation in any problem, you have to find this out, that whether your problem is actually fits with the approximation you are going to apply. So here the physicist only can respect the approximation or the constraints of approximation and the problem whichever he goes to solve. So here, not that there is a mathematical limit, or there is a mathematical region that is beyond the value of this. You can't apply WKB approximation. You can apply WKB approximation in any problem but you have to remember that the problem in the region wherever you are going to apply this approximation, the potential is not a drastically varied one. It is varying slowly, but it varies. It is not a constant one, because if you find a constant potential, you just don't go to apply WKB approximation, because we are in the graduation level. We have already came across the problems in which the potential is a constant one. But now, if the potential goes on increasing, or it goes on decreasing, you can apply this approximation, but keeping in mind that potential should be slowly varying. Okay. Now the equations. Now the equations. No, Shikha Chaudhary. I have just finished the discussion here. So just moving on, the equations connecting the WKB wave functions in the classical and in the non-classical regions. In the classical and in the non-classical regions are known as the connection formula. So now we are going to find out if there is some formulas in which we can actually tag these two regions. Okay, so these are known as the connection formula. So these connection formulas are meant for the classical as well as the non-classical region. Now, here also we are assuming a smoothly varying potential or a slowly varying potential. Now, as the potential is slowly varying, that Vx can be expanded in a Taylor series. Here also we are neglecting the higher order terms, that is Vx can be written as Vx1 plus del V del x at x equals to x1 into x minus x1. Let it be equation 17. Now this assumption amounts to approximating the potential by a straight line, as because I have assumed that the potential is a smoothly varying potential or smoothly varying function. So that potential Vx can be expanded in Taylor series, and this assumption amounts to approximating the potential by a straight line. So a curve potential is actually approximated as a straight line. Now at x equals to x1, that is the potential V at x1 is actually equals to E. So the Schrodinger equation near x equals to x1 is d2 psi dx2 plus twice m by h cut square e minus vx psi equals to 0. So the particle is moving from region 1 to region 2, and in region 1 E is greater than Vx. So I have taken Schrodinger equation as twice m by h cut square E minus Vx psi equals to 0. Now putting Vx as I've expanded it in Taylor series. So this is twice m by h cut square. E minus Vx becomes V of x1 plus del V del x at x equals to x1 into x minus of x1 psi equals to 0. So just putting the value of Vx here. Now here in the region, that is in the classical turning point, that is at x equals to x1, the value of Vx1 is actually E. So we can write it as d2 psi dx2 plus twice m by h cut square, and it is E minus, so the Vx1, that is the potential at the point x1, is actually E. So I am putting the value as E, and then minus del V del x at x equals to x1, into x minus x1, then psi equals to 0. So here I can neglect this E. So we have d2 psi dx2. So we have d2 psi dx2 minus twice m by h cut square del v del x at x equals to x1 into x minus x1 psi equals to 0. This is equation 18. Now as the first step, we have to work out the independent solutions of equation 18. The independent solutions of equation 18 for the regions x less than x1. For the region x less than x1, that is the region in which E greater than Vx. And x greater than x1, as this is a quadratic equation, you find it that this is a quadratic equation of psi. So we have two sets of solutions. One solution, or each set has two values of psi. One is, that is a pair of solutions for E less than Vx or x less than x1, and a pair of solutions in x greater than x1 region. So this is our first step, that is we have to work out independent solutions of equation 18 for the regions x less than x1 and x greater than x1. So in x less than x1 there should be two solutions, as well as for x greater than x1 there also be a pair of solutions, or there also be two solutions. Now this is our first step. Now the second step, uh, the next step is to carry these solutions to regions where Wkb approximation or the Wkb solutions are applicable, and then to obtain those connection formulas. So now the next step is to carry these solutions to regions where Wkb solutions are applicable, and then to obtain connection formulas. Now, suitable connection formulas are given in every book. You can find the connection formulas, and for you, I can write these equations. Now you have to memorize. Now this is not a very easy formulas. These are not very easy formulas. The formulas are 2 by root of k sine integral x to x1 k dx plus pi by 4, and the connection formulas, that is these are the connections 1 by root k e to the power or exponential minus x1 to x k dx This is a connection formula, equation 19, and the other one is 1 by root of k cos integral x to x1 k dx plus pi by 4, and this will connects to 1 by root k exponential, that is e to the power plus of integral x1 to x k dx, and this is equation 20. So the WKB solution given by 2 by root of k sine integral x to x1 k dx plus pi by 4 in the region x less than x1 goes over. So these are the connection formulas given as equation 19 and equation 20. I have told you that these equations you can get it in any standard quantum mechanics books. I have written these equations for you. You can write it down. Now, whatever these equations actually tells us, that it say if the WKB solution is given by this, if the solution is given by this in the region x less than x1, it goes over to an exponentially decaying solution in the region x greater than x1. So a solution of this type in region x less than x1, that is in the classical region, it will move on to region 2, that is the non-classical region, with an exponentially decaying term. And again, if the solution is 1 by root k, if the solution is of the type 1 by root k cos integral x to x1 k dx plus pi by 4, it will move on to region 2, or it will move on to the region x greater than x1 with an exponentially amplifying solution. Okay. 19. Is it okay? Now this is, I think there is a reflection. Shilpa, actually there is a reflection of my tube light here. So it is actually e to the power minus integral x1 to x k dx. Actually, this is the term it is also written in equation 20, but here the difference is, here there is a positive and here it is a negative one. So a negative one term means that, a negative equation terms mean that this is actually an exponentially decaying term, whereas with a positive sign, it actually tells us that this is a amplifying term. So so far we have completed WKB approximation method, where we have to apply this WKB method. How the method is derived, I have explained it. I think I can explain you to all. And then I have raised a problem. As because there are regions in which this classical and quantum, this classical and non-classical regions are combined, and there should be an interface from which a classical particle or a classical region and a quantum region can be connected. Now, this is the area in which actually WKB approximation fails, and how to remove this problem, that is, whenever this type of region occurs or this type of region appears, what you have to do. Now we have to make some connection equations, and then only the WKB approximation is valid. So I can't, already I have taken exactly 1.5 hour time. I think I should discuss you another method in which the WKB method validity, that is validity of WKB method. So you have to just go through it for any book, and you find it that the validity of WKB method is also important. So you have to, it is a short topic, so just go through it. I think there will be no problem for you to go through that validity of WKB method. অঙ্কিতা স্যার কোয়ান্টামের সিলেবাস আর এমসিকিউ কিরকম হবে স্যার একটু যদি ওভারঅল ডিসকাস করেন খুব ভালো হয়। I think already you get the routine of your exam, not the internal but the final exam, and I think it will be from 13th of March, so only 1 month is left. Though it is an online exam, but না ইন্টারনালের ব্যাপারটা সবার এত চিন্তা করার কিছু হয়নি। জাস্ট নাও এই অনলাইন এই ক্লাসে লাইভ স্ট্রিমিং এ আমি ইন্টারনাল নিয়ে অত আলোচনা করা উচিত না, বলা ঠিক হবে না। এটুকু শুধু বলে দিতে পারি যে খুব প্রবলেমেটিক নয়। আমি অলরেডি বোধহয় ফার্স্ট পেপার সেকেন্ড পেপারের সিলেবাস তোমাদেরকে দিয়ে দিয়েছি। আমি আজকে আসলে ফোর্থ পেপারের সিলেবাসটা আমি এখনো পাইনি আমার কাছে। ফোর্থ পেপারের সিলেবাসটা পেয়ে গেলে আমি সেটা দিয়ে দেবো। আমি আজকেই চেষ্টা করছি থার্ড ফোর্থ এবং ফিফথ পেপারের সিলেবাসটা দিয়ে দিচ্ছি, দিয়ে দিতে প্রবলেম হবে না। এমসিকিউ নিয়ে বা ইন্টারনাল নিয়ে ইউ ডোন্ট হ্যাভ টু বদার, খুব সমস্যার কিছু নেই, ভালোই মার্কস হয়ে যাবে আমার ধারণা। ম্যাক্সিমাম অফ ইউ শুড গেট দ্য ফুল মার্কস। ওকে, জাস্ট ডোন্ট বদার ফর ইট, জাস্ট গো অন for studying and prepare for the final exam to come in the March. Okay, so আজকেও শুধু ফিডব্যাক প্রতিদিন যেরকম দাও সেরকম একটা ফিডব্যাক যদি গ্রুপে পাই, so it will be so kind of you. Okay, টাটা।